In 2019, astronomers made a measurement that broke physics. They calculated how fast the universe is expanding and got two different answers. Both can't be right. One of them has to be wrong. Except they're both correct. The solution is almost too bizarre to believe. We're inside a hole, not a black hole, something else. A cosmic void, nearly 1 billion light-years across, where the laws of physics work differently than the rest of the universe. And we never knew because we've been inside it our entire existence. Let's start with a number that's tearing cosmology apart. The Hubble constant. It measures how fast the universe is expanding. Sounds simple, right? Measure the expansion rate, write it down, move on. Except we can't agree on what that number is. When astronomers measure nearby galaxies using supernovae as distance markers, they get one answer, about 73 kilometers per second per megaparsec. That means, for every 3.26 million light-years of distance, objects are moving away from us 73 kilometers per second faster. But when cosmologists measure the ancient light from the Big Bang, the cosmic microwave background radiation, they get a different answer, about 67 kilometers per second per megaparsec. That's a 9% difference. In science, especially cosmology, 9% might as well be infinity. These measurements are precise. The error bars are tiny. This isn't a rounding issue. Both methods are valid. Both have been checked and rechecked. Both should give the same answer because they're measuring the same universe. But they don't. This is called the Hubble tension, and it's not getting better. As measurements improve, the discrepancy becomes more obvious. Something is fundamentally wrong with our understanding of the universe. At first, scientists thought it was measurement error. Check the instruments, recalibrate, run it again. They did. The tension remained. Then they thought maybe dark energy, the mysterious force accelerating cosmic expansion, is changing over time. But that requires rewriting fundamental physics. Then came a more unsettling possibility. What if both measurements are correct, but we're not living in a typical part of the universe? What if our local region of space is different? What if we're inside something that affects how we measure cosmic expansion? What if we're inside a hole? Here's something they don't tell you in school. The universe isn't evenly distributed. It's lumpy, really lumpy. On small scales, you have planets orbiting stars, stars clustered in galaxies, galaxies grouped into clusters. But zoom out further, and the lumpiness continues. Galaxy clusters connect via filaments of dark matter and gas, forming a cosmic web spanning billions of light-years. And between these filaments? Nothing. Vast empty regions called cosmic voids. These aren't just empty space. They're regions with significantly lower density than average. Less matter, fewer galaxies, less dark matter. The biggest known void, the Botas void, is 330 million light-years across and contains only 60 galaxies. A typical region that size should contain 2,000 galaxies. It's not completely empty, but it's eerily underpopulated. Now here's where it gets interesting. In 2013, astronomers noticed something strange. Our Milky Way galaxy sits near the edge of a massive underdense region called the KBC void, named after astronomers Keenan, Barger, and Cowie who identified it. The KBC void is gigantic, nearly 1 billion light-years across. And we're not just near it, we're inside it. Imagine living your entire life in a valley and assuming the whole world is at that elevation. You measure air pressure, temperature, gravity, and everything seems normal because you have no other reference point. Then one day you climb a mountain and realize everything you measured was specific to the valley, not universal. That's our situation. We've been measuring the universe from inside a cosmic hole, assuming our measurements represent everywhere. They might not. Inside a void, matter density is lower. That affects gravitational attraction. Less matter means weaker gravity pulling things together, which means expansion can proceed faster locally. So, when we measure nearby galaxies, we're measuring expansion inside the void, where it's faster. When we measure the cosmic microwave background, we're seeing the average expansion rate of the entire universe, which is slower. Both measurements are correct. We're just measuring different things without realizing it. Let's talk about how cosmic voids form, because it's weirder than you'd think. In the early universe, matter was distributed almost uniformly. Almost. There were tiny density fluctuations, quantum variations that got stretched during cosmic inflation. Some regions had slightly more matter, others had slightly less. Gravity amplifies these differences. Regions with more matter attract surrounding matter, becoming denser. Regions with less matter lose matter to denser areas, becoming even emptier. Over billions of years, this process creates structure. High-density regions become galaxy clusters and filaments. Low-density regions become voids. But voids aren't static, they're expanding. As matter drains out toward the surrounding filaments, the void grows. And inside the void, the expansion rate of space itself is faster because there's less gravitational resistance. Think of it like traffic. On a crowded highway, cars move slowly because they're packed together. On an empty highway, traffic flows fast. Dense regions of the universe expand slowly because gravity resists. Empty regions expand faster because there's nothing to slow them down. Now, the KBC void we're inside is particularly large and underdense. Studies suggest it has about 20% less matter than the cosmic average. That might not sound like much, but on cosmic scales, it's significant. And here's the kicker. If we're inside a void, everything we've measured about the universe's expansion is biased. Every calculation based on local observations might be wrong. The Hubble constant we measure locally reflects void expansion, not universal expansion. Our understanding of dark energy might be skewed. Our calculations about the universe's age, its ultimate fate, the amount of dark matter, all potentially biased by our location. It's like trying to understand ocean currents by only measuring the water in a swimming pool. You'll get data, but it won't represent the ocean. Some cosmologists have run simulations to test this. They modeled observers inside voids measuring expansion rates and comparing them to cosmic microwave background measurements. The simulations produce exactly the kind of discrepancy we're seeing. The math works. The physics works. The idea that we're inside a cosmic void could solve the Hubble tension without breaking any laws of physics. But it creates an uncomfortable philosophical problem. For centuries, science has operated on a principle called the Copernican principle. We are not special. Earth isn't the center of the solar system. The sun isn't the center of the galaxy. Our galaxy isn't the center of the universe. We're a typical planet, orbiting a typical star, in a typical galaxy, in a typical region of space. This principle has guided cosmology for decades. It's why we assume our measurements represent the universe as a whole. If we're typical, then what we see locally should match what's happening everywhere. But what if we're not typical? What if our location inside a massive void is unusual? Statistically, most galaxies exist along filaments and in clusters, the densest regions of the cosmic web. Voids occupy more volume, but contain far fewer galaxies. Finding ourselves inside a void is somewhat unlikely. Not impossible, just unlikely. And this makes scientists uncomfortable because it violates the Copernican principle. If we're in an unusual location, it suggests something special about our position. And in science, special is a red flag. When Copernicus proposed that Earth orbits the Sun, he was removing humanity from the center of the universe. When Hubble discovered other galaxies beyond the Milky Way, he was showing we're not unique. Modern cosmology has fought hard to avoid anthropocentrism, the idea that humanity is cosmically significant. But now we might have to accept that our location is atypical, not because we're chosen or special in any meaningful sense, but because observers have to exist somewhere. And wherever they exist, they'll make measurements biased by their location. This is related to something called the weak anthropic principle. We observe the universe from a location compatible with our existence. If the universe were hostile to life everywhere, we wouldn't exist to observe it. So by definition, We find ourselves in a region where conditions allowed life to develop. Maybe that region happens to be inside a void. Maybe voids are unusually good places for galaxies like ours to form. Maybe something about lower density environments favors planetary systems and biological evolution. We don't know yet. But if true, it means every civilization in the universe faces the same problem. Their local measurements are biased by their location. They all measure a Hubble constant that doesn't match the cosmic average. Everyone thinks the universe is expanding at the rate they measure locally, but they're all wrong in different ways. Of course, the cosmic void hypothesis isn't the only explanation for the Hubble tension. Let's look at the alternatives, because some of them are even stranger. One possibility: dark energy is evolving. The cosmological constant, which drives cosmic acceleration, might not be constant. Maybe it changes over time or varies from place to place. This would require new physics beyond general relativity. It would mean Einstein's equations are incomplete, that there's some field or force we haven't discovered yet. It's possible, but it opens a Pandora's box of complications. Another possibility: dark matter is weirder than we think. Maybe it interacts with itself in ways we haven't detected. Maybe it decays over time. Maybe its distribution affects expansion rates differently than our models predict. Again, this requires rewriting fundamental assumptions. We'd need new particles, new interactions, new physics. Some physicists have proposed early dark energy, a form of dark energy that existed in the early universe but dissipated over time. This could alter the cosmic microwave background predictions and resolve the tension. But this is ad hoc. We're inventing new physics specifically to solve one problem. That's not how science prefers to work. Then there's the possibility that our measurements are still somehow wrong. Maybe supernovae aren't as reliable as we think. Maybe cosmic microwave background analysis has subtle errors we haven't caught. Many scientists have checked. The measurements hold up. But it's always possible some systematic error is lurking. The cosmic void explanation is appealing because it doesn't require new physics. It uses known physics, general relativity as it stands, to explain the discrepancy. It just requires accepting that our location is somewhat unusual, which is more likely that we're inside an atypical region of space, or that we need to rewrite fundamental physics. Different scientists have different opinions. The debate is ongoing, and it's getting heated. Let's step back and think about what it means if we're really inside a cosmic hole. First, it means every measurement we've made about the universe's expansion is biased. The Hubble constant we've been using is wrong for the universe as a whole. It's right for our local region, but not universal. This affects calculations about the universe's age. If expansion is actually slower on average than we thought, the universe might be older than 13.8 billion years, or younger, depending on how the corrections work out. It affects our understanding of dark energy. If local expansion is faster due to void effects, we might be overestimating dark energy's strength. The universe might not be accelerating as fast as we think. It affects predictions about the universe's ultimate fate. Will expansion accelerate forever until galaxies are isolated islands in an empty void? Or will something else happen? Our predictions depend on accurate measurements we might not have. Second, it means astronomy is harder than we thought. We can't just measure the nearby universe and extrapolate to the whole cosmos. We need to account for local structure, which means more complex models and more uncertainty. Third, it raises a disturbing question. What else are we wrong about? If our position inside a void biases expansion measurements, what other measurements are biased? Is our understanding of galaxy formation skewed? Our models of dark matter distribution? Our estimates of how common habitable planets are? Every measurement ever made was taken from inside this void. We have no external reference point. It's like being born colorblind and trying to study color theory. You can learn the physics of wavelengths, but you're missing something fundamental. And here's the existential aspect. If we're inside a void, we're in a relatively lonely part of the universe. Fewer galaxies means fewer stars, fewer planets, potentially fewer civilizations. Maybe that's why we haven't detected alien signals. Maybe most intelligent life exists along the filaments, in the dense clusters where galaxies are packed close together. Maybe voids are cosmological deserts where intelligence rarely arises. Or maybe it's the opposite. Maybe voids are safer, less radiation from nearby supernova, fewer gravitational disruptions from passing stars, more stable environments for complex life to evolve. We don't know, but our position inside a void might be central to understanding why we exist at all. So here we are, floating inside a cosmic hole nearly 1 billion light-years across, measuring a universe we can't fully see, making assumptions that might be fundamentally wrong. It's humbling. For all our technology, all our sophisticated instruments and precise measurements, we're still prisoners of our location. We can only see the universe from here, and here might be unusual. The Hubble tension might be solved by accepting this uncomfortable truth. We're not in a typical place. Our measurements don't represent the universe as a whole. We're inside something that warps our perspective. And maybe that's okay. Maybe every civilization faces this problem. Maybe everyone measures a biased Hubble constant. Maybe the universe is fundamentally difficult to understand from any single vantage point. But we're trying. We're asking the right questions, building better instruments, checking our assumptions. We're acknowledging that we might be inside a cosmic hole and working to correct for it. That's pretty remarkable when you think about it. We're aware of our own limitations and actively working to overcome them. So yeah, we're inside a cosmic hole, but at least now we know it. And that's the first step toward understanding what it means. What do you think? Does it bother you that our entire understanding of the universe might be skewed by our location? Drop your thoughts below, and if you want more deep dives into the mysteries hiding in plain sight, subscribe. Because the universe is stranger than we imagine, and we're just getting started figuring out how strange.